Right, so on to self-assessment questions 5, the fifth sheet here. So we're going to have a look at a classic model of disease spread, and it'll be interesting to see what this produces in light of what we've seen with COVID. So we have a differential equation for S, the number of susceptible people, the differential equation for I, the number of people who are infected at any given time, and the differential equation for or, which is the number of people who have recovered at any given time. And there is a bit of logic to these equations, as I've tried to explain in the paragraph down here. Is essentially, people become infected by interacting with infected persons, but also people become uninfected by recovering. So there's a balance of a lot of things going on. And this kind of model really forms the basis of a lot of the COVID models that are out there, although the COVID models are quite a bit more complicated than these. But this was the classic one, developed a number of years ago. So what we want to do is code this into Berkeley Madonna. And I suppose that the thing here is there's more stuff to code, so there's more potential to go wrong. But I think the key thing is to stick to our process, and just be systematic about what we do. So I'll go into Berkeley Madonna now. I'll leave stop time and all that kind of stuff as it is. So we've got DDT of S equals something, DDT of I equals something, and DDT of or equals something. So the S is minus beta times S times I. So I'm going to just write out beta as beta. So minus beta by S by I. Don't forget to put in your multiplication sign. And then for the I, we've got beta times S times I. So people the rate at which you're increasing your number of infected people is determined by the interaction between infected people and susceptible people. So then we have gamma times I. So the number of people is who are infected declines in proportion to the number of people who are infected at any given time, and that's because they're recovering. And then we have the recovery rate, which should be gamma by I. Let's just double check that, but that's, yeah, exactly. Okay, so that's our three differential equations. Not complicated, but this is a classic type of differential equation model you get throughout bioprocessing, throughout a lot of biological modeling for infectious disease spread, but also pharmacology and things like that. So now we have our initial conditions. So the initial value of S, we're going to have, say, 100 susceptible people, and we're going to start off with one infected person. When I was just practicing this or making sure I was able to work through this problem, I initially started with I equal to 0 and nothing was happening, and it only dawned on me then, sure, how can anything happen if you've no infected people to start with? And then the initial value of or is equal to 0. Okay, so we have values of beta that I suggested, and let me see what they were. Beta 0.005 and gamma equals 0.02, I think it was. Yeah, I remember you don't have to call them beta and gamma. You could have just called that B if you wanted to make your code a bit shorter, and call the gamma G, as long as you're consistent and as long as you assign the values. So that looks all right. I'm going to make the stop time a bit higher, and that's one of the things when you start off and you do simulation, you don't really know the stop time appropriate one. What we want to do is generate a graph that really captures the behavior in a fairly clear way. So I'm going to run that now, and oh, that's nice, it's turned out to be perfect. So remember, I sound like a rugby player now, but let's use our process, and our process is always to have the code, the parameter window, and then the output. So let's look at what some of this is showing, and I click this so that I can see everything. So the number of susceptible people declines, and the reason for that is that the people who are susceptible are getting infected. So They change their class, if you like, from being susceptible to being actually infected, so they drop off. The number of infected people climbs, but then it starts to level off and go back down to zero. And that's because people are recovering. So, and that's really due to the fact that you have a limited population there. And this kind of issue came up a lot during COVID, when people were arguing that, even if we hadn't locked down, that, we would have got an increase in cases, but they would have started to drop anyway. And a lot of people on Twitter and the like kept making this point. And there is some truth to that. I mean, that you won't ever get a situation where the number of infected people just keeps increasing it forever, because people do start recovering. But the problem is, if it's a serious virus, there could be a lot of people killed in the process, unless you try to slow down the rate of infections. So it's a complex kind of problem. It's not easy to decide what we should have done. Certainly the initial lockdown, we definitely had to do that. But you could argue that when we had vaccines and that, we could have been a little bit more liberal, I suppose, in how we promoted it. But in general, with disease spread, that's what you see. You get this increase in your number of infected people, and then it starts to drop off because your people are recovering. Now, an interesting thing, and I might make this one of the projects that one of you might do after the first 6 weeks, is to maybe incorporate death in there and just see how the death figures would look. So, I mean, I'm not going to ask you to do that on your own. I'd obviously give you help and troubleshoot it with you, but it'd be an interesting way to modify the model. So let's just do a little bit of a numerical experimentation here. So I'll overlay the plots, and let's imagine we'll change the gamma. Let's make that 0.0. So gamma really quantifies the rate at which the number of infected people disappear because they're recovering. So if we make this bigger, we should be getting faster recovery rates, I think. So let's bear in mind so we're making gamma bigger. So in other words, the recovery should be faster. Yeah, so we can see the green was the initial recovery rates, and here the gamma, or the purple, is the new recovery rate with the higher gamma. So, and because we're getting higher recovery rates, we're getting fewer infections. So, that's an important aspect of modeling, that when you change the parameters, they should produce behaviors that make sense. If I change now the beta really represents the rate at which people are becoming infected. So if I make that bigger, let's make it 0.01. I should be getting more infections, or I should be getting infections to happen faster. And there we have it. So with the new value of beta, we're getting more rapid infection occurring. So just as you'd expect. So nice little model. I will think about turning it into one of the projects for one or more of you to do. Okay, so that's problem 1 on the 5th self-assessment problem sheet.